The following function models the maximum weight W that a person can bench press in pounds at the end of T weeks of working out. Complete parts A through C. We've got our function W of T equals 260 minus 130 e to the negative 0.5 t. So in part A, we want to find the maximum weight that this person can bench press initially. Okay, so initially is at time equals 0. So we're going to substitute in for time a 0. That gives 260 minus 130 e to the negative 0.5 times 0. If we simplify, that gives 260 minus 130 e to the 0, since negative 0.5 times 0 is 0. This is 260 minus 130 e to the 0, and e to the 0 power is 1. So this gives 260 minus 130, and 260 minus 130 will be 130. So initially, this person can lift a weight of 130 pounds. In part B, we want to know what is the maximum weight that this person can bench press after 4 weeks of lifting. So going back to my word problem, I just wanted to confirm here the units for time. And it says here that we have T weeks of working out. And this person is going to work out for 4 weeks. So we're going to allow T to equal 4. We'll substitute that into our function. We have W of 4 equal 260 minus 130 e to the negative 0.5 times 4. And I'm going to use my calculator to work this out. So in the calculator, I've got 260 minus 130, and I'm going to use e. This calculator has 2 e's. There's an e above the division here, and then there's an e above the ln. They're both in blue. And I'm going to use the one above the ln since I'm going to be typing into the exponent of that e. We have negative 0.5 times 4. So that gives 242 pounds. We're going to round to the nearest whole number on this, 242 pounds. So after some training, 4 weeks of training, we've been able to increase how much we can lift. I thought I'd take a second here to talk about this E that you see in the formula for the weight that we can lift, the maximum weight we can lift. And this E is not a variable, it's a constant. And E is approximately 2.718. It's a number that was observed in lots of situations related to exponential equations by a mathematician named Euler. And because of how much it was prevalent in these formulas, it was given that special name E, and now is used in many formulas. So I'm just going to show you in the calculator this E button. If we select second and then the division, we can see that your calculator has been programmed to know that E is 2.718, 281828, and there's no pattern to these digits. It goes on forever. Your calculator has been programmed to more digits than it's displaying right now. but these are the ones that we can see. So let's take a look at our last part, Part C. What is the maximum weight that a person can bench after 5 weeks of training? So this is going to give us a time of 5, and we'll substitute that into our formula, W of T. So we have W of 5 equals 260 minus 130 e to the negative 0.5 times 5. And we'll substitute that into the calculator. And that will give 260 minus 130 e to the negative 0.5 times 5. So we get a maximum weight of 249 pounds. So after 5 weeks of training, we're able to have a maximum weight of even more. Suppose that you have $3,000 to invest. Which investment yields the greater return over a 10-year period? 7.11% compounded daily or 7.2% compounded quarterly? So in this question, we're going to be using a formula, the periodic compound interest formula. And there are some key words in this problem that indicate we're using this periodic compound interest formula. We have interest being compounded daily and also compounded quarterly, and both of those are indications of using this formula. Let's take a closer look at the formula. The formula is A equals P times 1 plus R over N to the NT. Let's go through what each one of those variables stand for. We have P being the principal or the initial investment. So what that means is that you're going to have a beginning or initial amount of money that you start your account with, that you start your investment with. And that is our P in the formula, the principal. The R is the annual interest rate. So the interest rate that your investment will be earning is R. N, and this one is the one that most people get confused about. N is the number of compoundings in 1 year. So if you can relate it to having your own savings account, it might make a little sense to you. In your typical savings account, interest gets added into your account every month. And so if that interest gets added into your account every month, we would say that N is 12. It's the number of times in 1 year that the interest is added or your money compounds. For our problem, our interest is compounded daily, so that would be 365 times a year, and also quarterly, that would be 4 times a year. The next variable is time, and our time is given to us in years. And then the last variable in the equation is A, and A stands for the accrued amount. So this accrued amount will be your initial investment. So it'll consist of that initial amount of money that you put in plus any interest that you've earned. So this accrued amount is your principal plus any interest that's been added into your account. So let's read this problem one more time, and as we read it, start to identify what variables belong to these values in the problem. Suppose that you have $3,000 to invest. $3,000 is our initial investment, the amount of money we're going to start with. So that is our principal. We have a principal of $3,000. Which investment yields the greater return over a 10-year period? So 10 years is our time of our investment. So T equals 10. And we're going to be considering two different offers. We have one account that will pay us 7.11% compounded daily, or 7.2% compounded quarterly. So we might have an interest rate of 7.11%, or that interest rate might be 7.2%. If the interest is compounded daily, N will be 365. If it's compounded quarterly, N will be 4. So this identifies all the different variables in the problem and their values, and we want to find out which investment yields a greater return. So a greater return means more money on our investment. So we're going to use our formula for the two situations. We've got daily, 7.2% daily, and also I wrote that backwards. That's 7.11% daily, and 7.2% quarterly. So if we solve the formula for 7.11% daily, one thing I forgot to mention earlier is that when we use our percentage, we always turn it into a decimal value. So we're going to write this as 0.0711. So we'll use that in our formula. So in our formula, we would have A equals 3,000 times 1 plus 0.0711 over N, that's 365. Daily is 365 compounds in a year, to the N times T of 10 years. If we use an interest rate of 7.2%, that R will be 0.072 and N will be 4. So our formula would look like this. 3,000 times 1 plus 0.072 over 4 to the 4 times 10. We're going to type both of these in our calculator to see which one gives us the larger return on our investment. So the first one, we have 3,000 times 1 plus 0.0711 divided by 365 raised to the 365 times 10 power. So after 10 years, that $3,000 would grow to be $6,107.66. I rounded to the nearest cent. So $6,107.66. And then let's do the calculation for the other account. We're going to do 3,000 times 1 plus 0.072 divided by 4 raised to the 4 times 10, and that gives us $6,107.66. $123.96. So the account that gives us more return on our investment after a 10-year period is the 7.2% compounded quarterly. So the higher interest rate on this one gave us a better return. Now, if we allowed for a longer period of time, that might not be the case. So I just wanted to come back with the calculator for a second. And in case you don't have a calculator that will allow you to type everything in all at once, I want to show you how you can use your calculator and follow order of operations. So in this expression, I'm going to do what's inside the parentheses first, and then we want to follow order of operations and do the division before addition, and we apply exponents before we do multiplication. So I would start by doing 0.0711 divided by 365, and then hit enter. And then inside the parentheses, I would add 1. And then I'm going to apply the exponents. I'm going to raise this, and 365 times 10 is 3,650. And then I'll multiply that by the 3,000. And you can see we get the same answer, $6,107.66 if we round it to the nearest cent. How much more will investment of $15,000 earning 7% compounded continuously for 7 years earn compared to the same investment at 7% compounded semi-annually for 7 years? So you'll notice that in this problem we have a keyword, continuously, which means that we're going to use a different compound interest formula. This compound interest formula is the continuous compound interest formula. The previous one was a periodic compound interest formula, and we are going to be using that formula in this problem as well, because we do have the interest compounding semi-annually. That tells us that n is going to be 2. So let me write down that other formula for you. The other formula is A equals P times 1 plus R over N to the NT. And that was our periodic compound interest formula. And that value of N will be 2 because interest is compounded semi-annually. The other one says that interest is compounded continuously. So let me try to explain the difference between the two. When interest is compounded periodically, that means that the interest gets added into the account, and then you wait a period of time and more interest gets added into the account, and then you wait a period of time and more interest gets added into the account. But when interest is compounded continuously, that means there's no waiting period between adding the interest. You allow the interest to start accruing from the moment that you open the account. So you allow the interest to start adding up right away instead of waiting that period of time. Now, mathematically, that allows us to simplify the formula. And previously we've talked about what E is, and E is approximately 2.718. But where it comes from is this expression, 1 plus 1 over n to the nt, excuse me, not nt, just n. If we allow n to go to infinity, then this expression gets closer to E, that 2.718. And you'll notice that in our periodic compound interest formula, you see something very similar to that E formula. And so what happens is, as we allow the number of compoundings to increase, our formula changes to this one over here. So this formula is A equals P e to the RT. The A, the P, the R, and the T are all the same variables that we used in the previous formula. So P is the principal, the initial investment. R is the annual interest rate, T is the time, and A is the accrued amount. And yet the formula has gotten simplified to this value of E in the base. So because we allowed the number of compoundings to go to infinity, this is no waiting period between adding interest. That gives us this new formula for continuous compound interest. So let's identify the different values in this formula. We have an investment of $15,000. That is our principal. We have a principal of $15,000. And we're going to earn a 7% interest rate on both of these options. So our annual interest rate, R, will be 7%. We'll use that in decimal form, 0.07. In both accounts, we are going to let that money grow for 7 years. Our time is 7. And we're hoping to figure out which investment will yield more money. How much more will one investment yield over the other? So we're going to do both calculations. So for the account earning 7% compounded continuously, we're going to use the formula A equals P e to the RT. And for the account paying 7% compounded semi-annually, we'll use the periodic compound interest formula A equals P times 1 plus R over N to the NT. So let's substitute our values in. We have A equals 15,000, E to the 0.07 times 7 years. So that's for our first one, and then the other one is 15,000 times 1 plus 0.07 over N. Interest is compounded semi-annually, so we'll use N equals 2 to the 2 times 7. Let's put both of these in our calculators. And for the first one, we have 15,000 times E raised to the 0.07 times 7. And after 7 years, that $15,000 will have grown to $24,484.74. So $244.84.74. I rounded to the nearest cent because we're talking about money. So then let's calculate the other one. and we will have $15,000 times 1 plus 0.07 over 2 raised to the 2 times 7. We have 24,280 and 42 cents. 242.80 and 42 cents. So we want to know how much more will the investment compound continuously make compared to the investment compounded semi-annually. So we want to subtract these two values, 24,474.84 minus 24,280 and 42 cents. Let's see how much more we make by investing our money continuously. So we make $194.42 more. By investing in an account compounded continuously rather than one semi-annually. Okay, so I was trying to go off my memory looking at this calculator and typing in the answer, and I just noticed that I typed this, or I wrote down this number wrong from memory. So it should have been 244.84.74, and I wrote 74.84. So I need to make this correction. I'm going to highlight it for you so that you can see it too. So I got these two mixed up. It should have been 84.74. And then that means this one was wrong as well. So this should be 84 and 74. Okay, so let's type that again and see if we can get the right answer this time. So we've got 244.84.74 minus 242.80.42, and that gives 204.32. So we would make $204.32 more by investing in the account compounded continuously. In 1970, a wildlife resource management team introduced a certain rabbit species into a forest for the first time. In 2003, the rabbit population had grown to 7,338. The relative growth rate for this rabbit species is 23%. Use the exponential growth model, P of t equals P naught e to the kt, to answer the following questions. How many rabbits did the Wildlife Resource Management team introduce into the forest in 1970? And how many rabbits can be expected in the year 2021? So we're going to be using this population growth and decay model. And as stated over there, it's P of t equals P naught e to the kt. And at first glance, it might seem a little bit confusing, but this formula actually is very similar to one that we've seen before, and that is the continuous compound interest formula. So I'm going to write that continuous compound interest formula here and refer to it. That formula is A equals P e to the RT. Hopefully you kind of already see some similarities. Let's go one by one through each of these variables and remember what they are using the continuous compound interest formula. The value of P in our continuous compound interest formula is the initial amount of money that we invest. Now in this formula, the P naught is in the same position, and you'll see that P naught is the initial amount. This is going to be your initial population. So you're seeing that the variables, although they represent different things, it's very similar ideas. So the P in the first formula is dealing with money, and that's your initial or beginning amount of money. In the population growth model, P naught is our initial or beginning population. So in the same position, have the basically the same meaning. One's dealing with money and one's dealing with the population. The next variable we look at is the R. In the continuous compound interest model, this R stood for the interest rate, the annual interest rate. And in our model, we use the letter K instead of R, and this K is representing the growth or decay rate. So they're both rates. And then finally, we have the variable of T, and T represented time in years. And we also have a T in this position, and T represents time. Now in this formula, we're not restricted to only using years. You really have to pay attention to the word problem and what units are used. So we could have any unit of time here. The last variable is this one on the other side. We have A. In our continuous compound interest formula, this A represented the accrued amount. That was the principal plus the interest. In this formula, it stands for P, population, and it's going to be the population after that period of time. It's going to include your starting population plus any growth in the population. So it's very similar. So P is the population after a period of time. So let's go back to our problem and read it again, and let's try to identify what the different values are. In 1970, a wildlife resource management team introduced a certain rabbit species into a forest for the first time. In 2003, the rabbit population had grown to 7,338. The relative growth rate for this rabbit species is 23%. Use the exponential growth model to answer the following questions. So let's write down some known information. We have the growth rate, which will be our value of K. So K will equal 23%. And in 1970, that's when this team introduced the population, and that's going to be our P naught. And that also represents a time of 0. That's the beginning or the initial time. And then in 2003, the population was recorded to be 7,338. So that's going to be 33 years later, 33 years after 1970. So we can do that with subtraction. 2003 minus 1970 gives me 33 years later. So in this problem, it says, how many rabbits did the wildlife resource management team introduce into the forest in 1970? So what they want to know is what is P naught? So we're going to be able to solve this problem by substituting into our model. This number here is our P, our population after some period of time. Then we have this variable being our time. And we're going to be able to solve for that P naught. So let's see that work. We have P of t equals P naught e to the kt. This k we're going to use in its decimal form, 0.23. That's P of t, that's 7,338, is equal to P naught e to the 0.23 times 33. I'll divide both sides by e to the 0.23 times 33. And that gives P naught equals, and we'll type that in our calculator. So in our calculator we have 7,338 divided by e to the 0.23 times 33. And we have 3.7, so let's round that to 4. So we're going to start with an initial population of rabbits of 4 in 1970. But then in part B, we want to know how many rabbits can be expected in the year 2021. So we have now figured out the initial population, so we can update our model with that information. We have P of t being 4 times e to the 0.23t. So we're going to be able to answer this question as long as we know the time after 1970. So t equals 2021 minus 1970, and that's going to give 51 years. So P of 51 years, that's 4 times e to the 0.23 times 51, and we'll type that in our calculator. 4 e to the 0.23 times 51 gives a really big population, a really big rabbit population of 496,974, and let's round so it'll be 75. So 496,975. So after 51 years, that rabbit population has grown significantly. Thank you for checking out my videos. Have a great day.